Welcome to another episode of learning. Please like my videos and share them with your friends and colleagues. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Thank you. Right. We continue the discussion of the solutions of the problems that have appeared in the CSIR National Eligibility Test March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Real Analysis, and the problem is related to the uniform convergence of sequence of given functions. This question is placed in part C, which is a multiple select question. There may be more than one answer, and the question carries 4.75 marks. The question ID is 706544. This question is suitable for all these examinations. Right. The given question is, let f be a function from R to itself. It be a uniformly continuous function. This function from R to R is a uniformly continuous function. For each positive integer n and x belongs to R, let Gn and Hn be defined by Gn of x is equal to f of x plus 1 by n. Hn of x is equal to f of nx. Right. So, which of the following statements are necessarily true? By defining like this as above, we get a sequence of functions Gn n greater than or equal to 1 and another sequence of functions Hn n greater than or equal to 1. We are given four options. Option 1, the sequence Gn converges uniformly on any compact subset of R but not on R. But not on R. Option 2, the sequence Gn converges uniformly on R. Option 3, there exists a subsequence of the sequence Hn that converges uniformly on R. Option 4, for every compact subset K of R, there exists a subsequence of the sequence Hn that converges uniformly on K. Right. Let's now discuss the solution of the problem in detail. We have a uniformly continuous function f from R to R. Right. This is a very essential condition here. And given two sequences Gn and Hn, they are defined by Gn of x is equal to f of x plus 1 by n. Hn of x is equal to f of nx, where n belongs to the set of natural numbers, x belongs to the set of real numbers. Right. Right. We have a uniformly continuous function f to R. Every uniformly continuous function is continuous. Therefore, f is continuous on R. We have the sequence Gn, where Gn is defined as Gn of x is equal to f of x plus 1 by n. N belongs to n, x belongs to R. We will now discuss the uniform convergence of the sequence Gn. First, we find the pointwise limit if it is pointwise convergent. For any x belongs to R, limit n tends to infinity of Gn of x is equal to limit n tends to infinity of f of x plus 1 by n. But what is f? F is continuous Therefore, limit n tends to infinity of f of x plus 1 by n will be equal to f of limit n tends to infinity of x plus 1 by n. Why? Because f is continuous. And that will be equal to f of limit of x is x only, and limit n tends to infinity of 1 by n is 0. Therefore, it is f of x plus limit n tends to infinity of 1 by n, that is f of x. So, the sequence Gn converges pointwise to f. The limit function is f. Thus, the sequence Gn converges pointwise to f on R. Right, pointwise convergence, we got it. Let's now discuss about the uniform convergence. Now, f is uniformly continuous, it is given to us. We will utilize that one. Remember their definition. For every epsilon greater than 0, there exists a delta greater than 0, such that modulus of fx minus fy less than epsilon whenever modulus of x minus y less than delta. This delta, depends only on epsilon. Okay, no problem. Now, for any x belongs to R, modulus of Gn of x minus f of x. Gn of x is modulus of f of x plus 1 by n, yes, minus f of x. And this can be made less than epsilon when modulus of x plus 1 by n minus x less than delta. X cancels when 1 by n is less than delta. So, by the uniform continuity above, this can be made. This means modulus of f of x plus 1 by n minus f of x can be made less than epsilon when mod of x plus 1 by n minus x is equal to 1 by n, x cancels, less than delta. We choose an appropriate n to satisfy this one. So, choose a natural number capital N such that n greater than 1 by delta. You note that this choice of n is independent of x. Thus, modulus of Gnx minus f of x is equal to modulus of f of x plus 1 by n minus f of x less than epsilon for all n greater than or equal to capital N. Yes, this 1 by delta and all that adjusted. And this works for all x belongs to R. Yes, this n is independent of x. This works for all x belongs to R. Therefore, we got the uniform continuity, uniform convergence. Thus, the sequence Gn converges uniformly to f on R. Right. We move to the next slide for the options of 1 and 2. So, we have seen the sequence Gn converges uniformly to f on R. Call on option 1. The option 1 says the sequence Gn converges uniformly on any compact subset of R but not on R. But it is convergent, uniformly convergent to f on R. So, in this it is given but not on R. So, obviously option 1 is not true. Option 2, the sequence Gn converges uniformly on R. Yes, we have proved. Therefore, option 2 is true and option 1 is not true because it claims that the convergence is not uniform on R, but it is uniformly convergent on R. Leave about this one. This is not. Therefore, option 1 is not true. Right. This is the discussion related to the sequence Gn. So, we move to the next slide for the discussion about the sequence Hn. Right. We have the sequence Hn, where Hnx is equal to f of nx, n belongs to n, x belongs to r. We call on option 3. There exists a subsequence of Hn, n greater than or equal to 1, that converges uniformly on R. There exists a subsequence of Hn. For this, there is a subsequence that converges uniformly on R. Right. We give a counter example. And this counter example, this Hnx definition, f of nx, after seeing that one, this is the counter example, what we can think of. Let f of x is equal to x. Yes, it is uniformly continuous. It is well known. It is an identity function. It is uniformly continuous on R. Agreed. Then Hnx is f of nx will be f of x is equal to x, f of nx will be nx, n belongs to n, x belongs to R. Let hnk of x, k greater than or equal to 1, is equal to nk of x, k greater than or equal to 1, be any subsequence of Hn. This is any subsequence of Hn. For this subsequence to converge uniformly on R, first of all, it must at least converge pointwise for every x belongs to R. Is this subsequence converge pointwise for every x belongs to R? For x is equal to 1, if you say, this subsequence nk, this subsequence is nk, x is 1, nk, k greater than or equal to 1, will tend to infinity. Nk tends to infinity as k tends to infinity. Therefore, that is, this subsequence nk is divergent. It is not pointwise convergence. Pointwise convergence is not. We are not getting the pointwise convergence. This subsequence cannot converge uniformly on R, since it does not converge for every point in x in R. That means there is no pointwise convergence. So option 3 is not necessarily true. In this situation, this fails. Right. We move on to the last option, option 4. For every compact subsequence k contained in R, there exists a subsequence of Hn that converges uniformly on R. Right. So let us consider the same example, f of x is equal to x. It is well known. It is an identity function, therefore it is uniformly continuous on R. So Hn of x is f of nx is nx, n belongs to n, x belongs to R. We take a compact subset, namely k is equal to the closed interval 1 to 2. Now clearly k is compact because it is a closed and bounded subset of R. It is a compact subset of R. For each x coming from k, Hn of x will be nx, x coming from k, x coming from k, nx tends to infinity as n tends to infinity. X is coming from k. So that means to say the sequence Hn is divergent for each x belongs to n. For each x belongs to n. The catch is for each x belongs to n. The catch is for each x belongs to k. For each x belongs to k. This shows no subsequence of Hn is pointwise convergent on k. For each x belongs to k, this is divergent. Therefore, no subsequence of Hn is pointwise convergent on k. When there is no pointwise convergence, there is no uniform convergence. Therefore, no subsequence of Hn is uniformly convergent on k. So, your option 4 says, for every compact subset k contained in R, there exists a subsequence that converges uniformly on k. No subsequence of Hn is uniformly convergent on K. Therefore, option 4 is not true. Thus, summarizing all the options, the answer to this question is option 2. That is the detailed discussion of the solution of the given problem from the section real analysis related to uniform convergence of sequence of functions. Right. And in this extra uniform continuity is given, that is exploited, right, to get in option 2. Right. So, in a way, it is a little difficult question. Anyway, I am sure that you understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please join as a member. Please join as a member in my channel and support me and my channel. Please subscribe my channel if you have not already subscribed. Yes, I am sure I am going to meet all of you once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.